Hello. In this video we shall discuss about the discrete energy exchange by atoms and the events leading to the quantization of the orbits as well as the pre-Rutherford the pre-Sommerfeld Bohr-Sommerfeld hypothesis and also the experimental analysis drawn prior to the initiation of the quantum mechanical studies. Now, according to Bohr's theory, the allowed energy values of hydrogen atom form a discrete set. So the energy emitted or absorbed by an atom is always equal to the, the energy difference, that is supposedly del E, between two allowed energy values. So we have two allowed energy values and the difference is always going to be del E, and the energy exchange by an atom is therefore discrete and it cannot emit or absorb any arbitrary amount of energy. The emission of spectral lines is an indirect evidence of the discrete energy emission by atoms. When an atom is given a certain amount of energy, is provided in a certain amount of energy, it absorbs it and it is carried to a state of higher allowed energy level, and the difference obviously, as you can see, is del E. So there is the higher energy level uh, and the difference del E amount of energy is provided to it, and it takes up that energy and goes to that excited state, and from that state it comes back to the stable state, giving out the electromagnetic radiation which has the same amount of energy that is within that gap, that is del E. So del E amount of energy is given out, del E amount of energy was absorbed in the first place. Now usually what happens in that case is that there's inelastic collision with other atoms, ions or electrons during that period. The kinetic energy acquired by an electron or ion due to its acceleration through a potential difference is transferred inelastically to an atom. This is a convenient experimental method for study of energy absorption by atoms. But before going into any kind of experimental analysis, we would like to provide some nomenclature that is associated with the energy absorption. One of them being the ionization energy. Now it's very convenient to answer this case or this define this term, that is, ionization obviously means that you ionize a given atom. That means it loses a certain electron from its bound state, it becomes free. So the outermost electron, the valence electrons, are the ones which have the least amount of energy, are least bound to the nucleus, and as a result of that they are more prone to get out of their orbits, and they require least energy to do so. Now the energy that is required to just emit that electron out of that orbit, out of its own orbit, is what we term as the ionization energy. Now it must be bound to the orbit or to the nucleus in at a certain energy value. Let's say, for example, we have the case of electron in case of hydrogen atom, which is bound at an energy of minus 13.6 electron volts, and you can refer to the previous video that I've made on ionization energy, and it will be provided with that much amount of energy, the positive value of that, and the net energy therefore remains to be 0 electron volts means it is in the free state now. It doesn't have any excess energy so that it can travel or do anything, but it has just the amount of energy to come out of that orbit or that energy level that it was put in. Now, this was the bound state, and this was the energy that was provided to get it out of the bound state and hence ionize the atom, and hence this energy in that case is the ionization energy. Now, there's another case where we talk about the excitation energy. Now, the excitation energy is the one which will excite it to a certain other level. Now, if it was at minus 13.6 electron volt in one of the orbits, we know the higher orbit is having an energy supposedly to be equal to minus 3.4 electron volts, and the difference in that case is 10.2. So if we are providing it with an energy of 10.2 electron volts, then it will go from this energy level to this energy level, the higher energy level. It may be in the excited state, doesn't matter. We were obviously, the term that we can see is excitation, so we are exciting it to a higher energy level. We may excite it to some other higher energy level as well. If we are providing a greater energy than 13.6, say we are providing it with an energy of 14.6, then it has plus 1 electron volts. That means it is free. It no longer remains in any kind of energy level, and it is free to roam around with that energy of 1 electron volt, which means that it will be actually making a new energy level of 1 electron volt of free electrons. That is a separate topic of discussion. So this is more or less the case of excitation energy. This was again in one of the states. This is state 1, and then it got the energy to move to the second state, state 2, right? And it was excited by this excitation energy that was provided to it by some source or the other. Now, the corresponding potentials that were provided or that were available for such kind of acceleration of the electron, either the ionization, case of ionization, or the case of excitation, the potentials corresponding to them were the ionization potential and the excitation potential in this case. As you can see, the energy, it is convenient to note these energies at with that unit, that is electron volt, because electron volt makes it easy to convert it to the corresponding potential. In this case, the potential is simply 13.6 volts, and in this case it is simply 10.2 volts, because with the electron, the charge of the electron multiplied to it, it becomes the energy, because we know that potential times of the charge gives us the potential energy, which is the electrostatic potential energy. If the charge is in the form of the unit of charge, which is the electron, the charge of the electron, then we simply have to remove that E and we simply get the voltage corresponding to it. So it's easier in that way. It is convenient to represent the energy levels or the various energy cases of energy at the atomic level in electron volts. Now, a collection of all these potentials that we have studied is what we term as the critical potential. So these are collectively called as critical potentials. Now we can discuss about the Franck-Hertz experiment, which provided conformity to the existence of the discrete levels of atom. So let's get started with that. Now, a series of experiments were performed in 1914 by James Franck and Gustav Hertz on absorption of energy by mercury atoms in collision with electrons and they confirmed the existence of discrete energy levels of atoms. Let's see the experimental arrangement first. Now, in this experimental arrangement, I'll be providing you with the arrangement in with a bit of a diagram from my side. Then I'll provide you with the circuit diagram, which will be much easier to understand. Now, to start with, we had a cathode which was indirectly heated by a filament that was provided. So this was the heat that was provided by the filament to the cathode, and the cathode was then surrounded by a grid which was maintained at a certain potential, mostly positive potential. So obviously the potential can be controlled. So there was a grid which was in the form of a wired grid, netted wire, and that was, this is the netted grid that was provided. I'm not drawing that many lines so that it's easier for you to understand the diagram. So this is a form of a grid that was provided surrounding that, and it was maintained at a certain potential. As per the requirement, the potential can be varied, and then it was followed up with a plate. The plate can be of some material which will be opaque, but in this case I am providing you with a transparent view to so that you get to understand the arrangement. So from the cathode, which was provided with a filament to emit electrons, the electrons would be emitted, they would be accelerated through the grid towards the plate, and we'll be obtaining the plate current. So that was the process that was involved. Now the circuit diagram for this will be a bit easier, in the sense that we have understood this kind of a phenomenon in case of the photoelectric effect previously. So this is the arrangement where we have the cathode over here, the grid is provided in between the plate and the cathode. So this was the plate, and then the external circuit. Now this was placed within an evacuated tube, and then also mercury vapor was provided there, so that the experiment that was carried out was involving the collision of mercury atoms, as mentioned earlier. The grid was provided with a potential which could be varied. That's why we are providing that arrow in that case, which is telling us about the regulating potential that we may provide. And in the micro ammeter, we'll be observing the amount of current that will be flowing, and graphically we'll be able to explain the experimental outcome. Now, so this is more or less the arrangement, the circuit for that. The cylindrical plate is provided, and it is maintained at slightly negative potential with respect to the grid, of course. And the electrons reaching the plate, they contribute to the plate current, which is measured by a microammeter. And the plate, the cathode, and the grid are enclosed, as I said, in evacuated tube which is filled with mercury, but it is at very low pressure. And the plate current can be measured for different values of the accelerating potential. Now let's plot the graph that was obtained in this case, in the Franck-Hertz experiment. Now in the potential versus the current curve, as the accelerating potential V is increased from 0, the plate current also increases. But what is observed is that when the accelerating voltage becomes equal to 4.9 volts, it is what they observed. This is the 5 volt that I have drawn over here, so 4.9 will be somewhere behind that. And exactly at that point, the current which was increasing It increased to a certain peak value and there was a sharp fall of current over here. And from that sharp fall, it went down and then again upon increasing the potential further, it increased, but again at a value say 9.8, which is just behind that 10, it was increasing, but then again forming a peak, it again experienced a sharp fall. Similarly, at 14.7 as well, it was observed to experience a peak of some value, and then again there was a sharp fall that was observed in that case as well. So as you can see from here, 4.9, 9.8, 14.7, they are all in multiples of 4.9 volts. So multiples of 4.9 volts. That number 4.9 explains something. What did it explain? Well, the results of the Franck Hertz experiment, which were plotted like this graphically, tell us that the energy difference between the ground state and the first excited state of a mercury atom is actually equal to 4.9 electron volt. So what was the explanation for this kind of behavior? The first excitation potential, that is 4.9 volt, when the potential was less than 4.9 volt, the energy of the electrons was less than the excitation energy of the mercury atom. So the atoms were not able to absorb the energy from the electron. They are not allowed to do that. The collision of the electrons with mercury atoms were elastic till this time, and they passed through the grid and reached the plate. So there was no problem with that. And the plate current, because as they were reaching the plate, so the plate current was also increasing with the increase in the accelerating voltage. The greater the voltage, the greater was the current observed, till it achieved that value of 4.9. When the energy of the electron became equal to 4.9 electron volt, they collided inelastically with the mercury atoms. Now this inelastic collision led to the transfer of their energy, because they were in an excited state, they had energy, they transferred that energy to the atoms which were excited to the next higher energy state. And as a result, because the electrons had now given out their energy, they were unable to reach the plate. And as a result of that, the plate current showed a fall or a dip in its value. There was a sharp fall in current. When the accelerating potential was further increased, the current again increased but showed sharp fall at voltages which were integral multiples of 4.9 volts, owing to the energy difference or the energy levels that were present in case of mercury atom. When the atom from the first excited state comes back to the ground state, we observe the value of energy that was emitted and the wavelength that was emitted. The wavelength that was emitted in this case was of value 2537 angstrom units. And guess what? The corresponding energy to this is going to give us the difference in energy, which is h nu, which is hc over lambda, and you put those values, plugging in those values, what you get is in electron volts, it is coming out to be 4.9 electron volts. You put the value of h, you put the value of c, and then also the value of the wavelength that was present or that was obtained from the radiation, and with those values converted to the electron volt unit, you get the value as 4.9 electron volts. So the Franck Hertz experiment with mercury vapor and many other corresponding experiments using different gases and vapors provided an excellent confirmation of the discrete nature of the atomic energy level. So that's it from this video. We'll be making a few more videos on such type of findings, such experiments. Till then, thank you for watching.